Alright, today we're going to be doing Unit 1, Lesson 6, all on inverse functions. A lot of this is going to revolve around notation and algebra, understanding what they're asking you to do and how you can properly answer it using especially a lot of the function notation. The first thing is we're going to find an inverse where we literally take what is x and y and we reverse the values. We don't change the signs, we just change their location within the table. The indicator of this in terms of notation is going to be f, the name of the function, raised to the negative 1x. Now this negative 1 is not an exponent like in the traditional sense where you would move something to a denominator. This is function notation. Okay? So when you see this does not mean take whatever the function is and put it in the denominator. This is a grouped function, it stays together. You have the name, you're told to find the inverse in terms of x. So let's take a look at example 1. This would be the simplest type. You've probably seen this before. It's very concrete in terms of the numbers. You're given 3 ordered pairs. 3 ordered pairs in a set are known as a relation. If you are asked to find the inverse, it means literally take x and y and reverse them. Reverse them, reverse them. They change locations. They do not change signs. They don't change quadrants. They just simply interchange the x and the y values. Now, this is not in your notes, but it would be great if you added this because I think it's going to make a lot of sense. Let's say we take these points here and we do a quick picture. So I have 0, 1. I have 2, 3. I have 4, 5. Okay. 3 points. Now what I'm also going to do is I'm going to just draw in a fancy looking like S. Okay, I'll put arrowheads on the end. Yours doesn't have to match exactly, that's okay. 1, 2, and 3. Whether I give you ordered pairs or I give you a picture where you have to pick out 3 points that you can easily match up to x and y values, when you're asked to calculate the inverse, the mechanical process is the same. So notice if 0, 1 is a point, the inverse was 1, 0. So now when I go to plot this, 1, 0 is going to be over here. 2, 3 became 3, 2. 3, 2. 4, 5 became 5, 4, which is up here. Very similar looking dots. They are not exactly the same. Okay. But what's interesting about this is that this graph now is going to actually kind of curve like this. It's going to be a mirror image. Okay. You're going to see this mirror image that exists. So what am I hinting at? You may be given a picture and told to come up with the inverse functions graph. You would choose 3 points, 4 points, 5 points, whatever you think is necessary. I would choose points that lie at the intersections of like integer values. I would invert them in a table or a list, and then I would plot those points. The next skill that we're going to work on is finding the inverse algebraically. We are going to switch the x and the y variables, and then we're going to resolve for y. Okay, it's very algebraic, very computational. So let's do that in the next example. So we're going to find the inverse of f of x equals x cubed plus 5. Now, just as a quick review, do all of you know what this graph would look like without a calculator? Yes? So if it were a multi-step problem on a test, part A could be graph without a calculator. How would you graph this? I would move the vertex up 5, right? So from my x and y axis, 1, 2, 3, 4, 5, dot, swoop down, swoop the other way. It would look like x cubed. So keep that in mind. Instead of using f of x, I'm going to replace f of x with our traditional y value. So I'm going to say y is equal to x cubed plus 5. I then invert x and y. Every place I have an x, I change it to a y, and every place I have a y, I replace it with an x. I then solve for y. So I'm going to subtract 5, and then I'm going to take the cube root. My last step is to indicate using function notation that f inverse is the cube root of x minus 5. That these two are inverses of one another. Too fast? Are we okay? All right, please put a star by the next one, example 3. Study this one. You need to know how to do one like it. You're going to have them in your homework. You're going to see one on the test. All right, following the same steps, I'm going to replace f of x with the letter y. I'm then going to invert or switch out all of my x's and y's. And I get to here. Okay? Now, if I take x and I put it over 1, do you all see this as a fraction equal to a fraction or a proportion? We went over these in the prerequisite unit. How do we solve a proportion of a fraction equal to a fraction? Yes, sir? Cross multiply. Okay? So we're going to cross multiply. It's going to look like 1 times y plus 1, x times y minus 2. Now, following PEMDAS, when we're on this green line of work, we need to get rid of parentheses. How would we do that? Distribute, okay? When we distribute, we're going to be left with 4 terms. I'm going to erase this line right here so you can see it. I'm going to be left with xy minus 2x, a y, and a plus 1. In order to solve for y, we have to group all of the y people or y terms on the same side. Okay, so notice I've got 2 people and 2 people. I want all the y people together, everybody else to the other side. Okay, so this is math segregation at its best. Here's what it looks like. Group the y people. Now this is the step that maybe isn't as familiar to you. Once you put all the y's on the same side, I want to factor out a y. Okay, I understand that the goal was to get rid of parentheses, but that's just so we could move people left and right. Move them on either side of the equal sign. Now when I take out the y, how can I isolate y? Divide by x minus 1. So I can divide by x minus 1 and then write my final answer using function notation. I'm going to give you a minute. I'd like you to try the next example on your own, and then I'll come back and take a moment to check your work in example 4, 2 separate methods to solve. All right, now we're going to talk about one of my favorite topics with inverses, which is the concept of one-to-one. On the board, I have 3 examples written, A, B, and C. Which of these are functions? On an SAT, it would be worded something to the effect of, which of the following relations are not an example of a function? Take a look, everybody look. Which are functional and which are not? Okay, show of hands. How many say A is a function? Nice and high. Nice and high, nice and high. Okay, A is a function. How about B? B is not a function. And C? Function. C is the easiest to identify. Remember, in functions, if we call X girls, Y boys, boys are allowed to be cheaters, girls are not. Okay? General, simple example. However, today what we're going to talk about is one-to-one. 1-to-1, when I look up here, over here, this is an example of 1-to-1. By definition, it just means that everybody's matched up and nobody's a cheater. It's like the perfect functional world. Okay? It's very easy to understand from that perspective when you're analyzing the actual numbers. Right? A function has an inverse that is also a function. So basically, if I would take A and I would invert it, do you agree that the inverted values would not form a function? It would look more like B then? Right. This is not an example of a 1-to-1 function. Yes, it's a function, but it's not 1-to-1. We come down to letter C, that is not the case. If I invert these, I still have a functional relationship that results. This is an example of 1-to-1. Now, we have a line test that we can use on an original function to determine whether or not that function is a 1-to-1. It's called the horizontal line test. So it's just like the vertical line test. If I take a horizontal line, pass it through the graph, if it touches at more than one place, it means the inverse is not a function, therefore the original is not 1-to-1. So this one would be 1-to-1. Absolute value passes the vertical line test. However, it does not pass the horizontal line test, which means its inverse is not a function. So this is not 1-to-1. Square root function passes the vertical line test, of course, it's a function, and it passes the horizontal line test, therefore it is 1-to-1. Parabola, pretty similar to absolute value, passes the vertical, does not pass the horizontal, therefore it is not a 1-to-1 function. Its inverse is not a function. X cubed passes vertical and horizontal. But I want to caution you about x cubed. There are examples that you will put into your calculator that end up looking like this when you graph them. If your x cubed function looks like that, that's an example of a polynomial function, that would not pass the horizontal line test, therefore it would not be a 1-to-1 function. So make sure you zoom in and look closely to find out exactly what's going on in here around the origin. Questions? All right. If you have a highlighter, this is a great time for that. In this next section, there are very specific directions for proof, for the burden of proof. Do you see in your notes, and I don't have this on the screen, so you're going to have to circle, highlight, put a bubble around it. Do you see where it says prove using composites? Look, in the example, prove using composites. This is an example of an application problem of the definition of a composite. Obviously, you're going to do 2 composite problems and do algebra with them, which means it's worth significant points on a test. You don't get to choose another method if it says prove using composites. Okay? So composites are f of g and g of f, this definition right here. So let's take a look at example 5. You are given an f function over here, and you are given a g function over here. You're going to calculate f of g, you're going to calculate g of f. If both of those simplify down to x using legal algebra, legal, not illegal, then you can prove to me that these 2 functions are inverses of each other. That basically if you look at their xy tables, you can invert them, and it would be the table of the other function. So, first thing that you're going to need to do is, you're going to need to calculate f of g. Then over here, you're going to have to calculate g of f. So you're going to have to do two separate calculations with legal algebra, and that seems to be the hookup for some of you. That's the bump in the road. So if I'm going to come over here, I want to go to the f function, and what am I going to plug in for x? What goes into the f function if I'm finding f of g? This thing, right? Okay, now be careful. I'm going to write this as x minus 1 up top, and I'm going to put the negative in the bottom with the 2. That way I don't lose it. You all know about the amazing floating negative, right, of fractions? Yes? If I have a fraction that's like 2/3, and I put a negative up here, I could write it out front, or I could move it to the bottom. As long as it's only one of them, it's the amazing floating negative. It can be in any of these places, and they mean the same thing. So for my bookkeeping sense, it's easy for me to just move that to the bottom since it's just a single constant in the bottom. So now I'm going to go to the f function, and every place I have an x, I'm going to replace it with x minus 1 over negative 2. So I write the negative 2. I'm going to put in the x minus 1 over negative 2 plus 1. What can I legally cancel through multiplication? The negative 2's, which leaves me with x minus 1 plus 1, which leaves me with just x. I'm looking pretty strong right now for an argument that these two are going to be functions of one another. Now I'm going to go to g of f. So I'm going to go to the g function. What do I plug into the g function? Negative 2x plus 1. So I go up here. I'm going to put that negative in the bottom, the amazing floating negative. I'm going to replace x with negative 2x plus 1. And I'm going to keep the minus 1. Now I always see this anytime a problem like this comes up. Is this negative 1 subtraction or multiplication? It is subtraction. Okay? We don't use distributive property with a negative 1 at the end. It would have to be in the front if I wanted you to multiply. So if I start up top here, what can I cancel? Positive 1 and negative 1 cancel, which leaves me with negative 2x over negative 2, which leaves me with x. This is a proof using composites. Questions on that? Yes, sir.
So when you get the two answers, what does that mean?
Okay, so what it means is here and here. Since you came out to the same, and they both came out to x, that tells you that these two functions, f of x and g of x, are inverses. In other words, I could write this as f inverse of x if I wanted to instead of using g of x. They're inverses of one another. Okay. All right, let's skip the u-try right now. Let's go to the bottom. And let's talk about testing inverses graphically. All right. So here's the game. Let's say that this is f of x, and let's say that this blue line is g of x. I know that the two of those are inverses graphically. If I draw in the line y equals x, and I end up with a mirror image. Take a look at that. Red is the mirror image of the blue. That means that the two of them are inverses. Okay? Okay, so however you want to draw that, that is, I believe, the first one coming up. Example 7. Try graphing example 7 and tell me if this is the picture that you get. This is example 7. I want you to put it in because I also want you to double check you know how to put fractions in the calculator correctly. Think about it. If in example 7 you put the fraction, the root in incorrectly, you're going to tell me it's maybe not inverses, and it is, you're only a lot more points. Try putting it in and see if this is the picture that is generated. Is that so? What's happening? This is good that it's happening now. It's what you're putting in the calculator. I think f of x is pretty easy to enter. G of x. You need to tell it to use the cube root function, which automatically gives some of you the opening parenthesis. Okay? This set of parentheses here, this opening parenthesis, has to do with everything that you want underneath the root, because I don't think that continues in some of your calculators. That's why I'm going to need an ending parenthesis at the end to indicate all of that was under the root, but then I need the numerator offset divided by 2. Okay, so if you didn't remember to do that, please write it down underneath the graph. Make sure you put a little note like study how to enter fractions so you don't forget and make those mistakes on the test. Okay? If you do that correctly and you fix it, it should look like my picture. Okay. Now, in your calculator, go into the setting that says, let me stay on this for 1 second. It says Zoom. Choose Zoom 5. Zoom 5 is going to be the square setting. What it does is it just rescales it to make it look a little bit nicer. If you wanted to, you could even put in a y3 equal to x, which would be that line. Do you have a mirror image? What do you think? When you put that in, do you have a mirror image? Yes? Yeah. Yes. Okay, so underneath you can write yes, that's an example. That's how you would do it graphically. So we can prove two functions are inverses algebraically using composites, or we can prove it graphically using our graphing calculator and verifying the mirror image. Questions on that? Okay, now at the bottom I just have a little caveat here, kind of to connect all the dots. How do we know if a function is one-to-one? What makes a function one-to-one? Silence. Yes. The original function has to pass the horizontal line test. Correct. What if you didn't have an equation and you had a table? How do you determine if something is one-to-one? Correct. That there are no repeaters x or y that match up. Okay, that's the easiest way to kind of look at that. Okay. All right, questions I could ask you on the test. How would we conclude graphically if a function is one-to-one? What would be the answer to that? How do we know? Horizontal line test. Sounds good. Number 2, how can we algebraically find a function's inverse? Here's a function. What's its inverse? Invert x and y, resolve for y. How can we prove algebraically that two functions are inverses of each other? Use composites. Find f of g, g of f, make sure they both reduce back to x. What do we look for when graphing two functions to determine if they are inverses of each other? So you have the pictures of f and g. See if they're on the xy line, if they are a reflection. Okay? That's the summary of everything we went over in today's lesson.